When two objects are in contact, one object exerts a force on the other in a direction that's perpendicular, that is normal to the surface of contact of the other object. So you'll sometimes see the word normal being used, or normal force. It's a force perpendicular to the surface of contact of the object. Let's suppose we have a book resting on a horizontal table. We are going to get the contact forces between the book and the table. Let's consider the forces acting on the book. Well, we have the weight of the book, or the force of Earth's gravity on the book, that acts vertically downwards. This vector is actually pointing towards the center of the Earth. Now, in the last video we introduced this useful notation. We can refer to this vector as FBE, where B stands for book, E stands for Earth. So this is the force on the book due to the Earth. In other words, it's the weight of the book. The magnitude of this vector would be mg, where m is the mass of the book. Now the book is at rest, so this can't be the only force acting on the book. If this was the only force acting on the book, then by Newton's second law, the book would accelerate in the direction of this force. And the acceleration would be given by the magnitude of the force divided by the mass of the book. Since the book is at rest, the resultant force acting on it must be zero. We must have another force acting on this book that has the same magnitude but is opposite in direction to FBE. Now this force must be the force on the book due to the table, because if we remove the table, this force doesn't exist. The book will have just a force of FBE acting on it, just a single force acting on it. Obviously we have two forces acting on the book, and the sum of these two forces is zero. So here's the resultant force F acting on the book. We just get the vector sum of these two forces acting on the book. That must be zero because by Newton's second law, the resultant force on any object is the mass of the object times the acceleration of the object. But since the book is at rest, the acceleration is zero, so the resultant force is zero. So FBT is equal in magnitude but opposite in direction to FBE. Now I need to emphasize strongly that this relation here is not Newton's third law. In the previous video we saw a vector relation that looks exactly like this. We saw one vector on one side equal minus another vector on the other side. Okay, Newton's third law says something different. It looks superficially the same. This thing here is actually an application of Newton's second law applied to an object at rest, an object whose acceleration is zero. So these two forces do not constitute an action-reaction pair. It's just a consequence of Newton's second law with an object at rest. FBT is a contact force. It's the force on the book due to the table. Now we can apply Newton's third law and consider the force on the table due to the book. So here is FTB. By Newton's third law, FBT is equal to minus FTB. So these two forces here, shown here in blue, do constitute an action-reaction pair. So these are the contact forces between the book and the table. The force on the book due to the table and the force on the table due to the book. If you want to find another action-reaction pair, we have to consider the force on the Earth due to the book. Okay, so we have a force on the book due to the Earth. That's a gravitational force actually. And by Newton's third law, there must be an equal and opposite force on the Earth due to the book. Okay, we saw that in the previous video with the case of an apple hanging on a tree. So here's an action-reaction pair. Now the magnitude of FBE is equal to mg, and the magnitude of this force is also mg, where little m is the mass of the book. We see no mention of the mass of the Earth here. Now this action-reaction pair involves gravitational forces. See, there's no contact between the book and the Earth. Well, unless you include a table as part of the Earth, I suppose we could talk about a contact force, but the book could be hanging from something, and the book doesn't have to make any contact with the Earth. So by earth here, we could just mean everything underneath the book except the table. We could just remove the table, and then you can see that the book and the earth are not in contact. The table is going to make no difference to this problem really, because its mass is so tiny compared to the mass of the earth. So we see that only in the case where the surface of contact is horizontal is FBT equal to FBE as a consequence of Newton's second law. In general, that's not the case. Let's look at a book on an inclined surface. Okay, as before, we have the weight of the book, or the force on the book due to the earth. That the magnitude of that vector hasn't changed. That vector is still the same. Its magnitude is mg and is pointing vertically downwards. Little m is the mass of the book. I'll just remove that because that's not too important to what we're doing here. Let's consider the contact force on the book due to this surface here. I'll still refer to this surface as a table. It's a table that's been slanted or inclined. So I will call the force on the book due to the table FBT. So this force is perpendicular or normal to the surface of contact of the book and the table. In this situation, the magnitude of FBT is actually less than the magnitude of FBE. In the other situation, these two forces were equal in magnitude. Now the reason that that's true is because this book has no acceleration in a direction perpendicular to the incline. So if we get the components of the forces on the book acting in a direction that's perpendicular to the table, those components must sum to zero. Okay, there could be friction acting as well to prevent the book from sliding down the table, but friction force has no component perpendicular to the table, so we're not interested in the friction force. That force is parallel to the table. We're only interested in the components of the forces acting on the book in a direction perpendicular to the table. So these two forces are the only two forces that have components perpendicular to the table. Well, FBT is entirely in a direction that's perpendicular to the table. So the component of FBT in a direction perpendicular to the table is FBT itself. However, the component of this force perpendicular to the table is got by projecting the tip of this vector onto a line perpendicular to the table. So here's the component of FBE perpendicular to the table. And of course this projection is smaller in magnitude than FBE. And this projection must equal FBT if the book has no resultant force in a direction perpendicular to the table. So the book is not accelerating in this direction for sure, and is certainly not accelerating in a direction perpendicular to the table. So the resultant force, the component of the resultant force in a direction perpendicular to the table is zero. So in other words, the magnitude of this force must equal the magnitude of this force here for them to cancel each other out. But since this force is smaller in magnitude than FBE, then it must be the case that FBT is smaller in magnitude than FBE. Finally, I just want to mention that contact forces between two objects are electrical. Now that does not mean that the two objects are charged. Okay, so when we had the book on the horizontal table, when I say the contact force on the book due to the table is electrical, I don't mean that the book has a positive charge and the table has a positive charge, so they repel each other. That's not the case. The two objects in contact with each other, the book and the table, are electrically neutral. They're electrically neutral overall, but at the microscopic level, if we look at what's going on at the interface of the two objects, then there is an electrical repulsion. There must be some sort of a repulsion, because otherwise the book would accelerate towards the center of the earth. The book would crash down through the table.